Okay, welcome everyone to my continuation of what is Magma or Magma Mondays or Introduction to Magma, whatever you actually want to call it. Doesn't matter. So this is kind of the third video, video number 2, but I've started counting at 0. And again, there's a link in the description. So I stole all of this in some sense from Don's lecture. The link to Don's video is in the description. And on the main webpage, I'm trying to give it a slightly different flavor. In particular, again, want to emphasize the usage of the online calculator, the one that you are seeing right now. Okay, so we're seeing the online calculator and we're going to use it. And the way we are going to do it is we are going to use the lecture notes as in the previous video. I hope the setting is quite clear. I kind of assume that you have seen one of the previous videos. If you haven't, probably this video is not your right choice for now. Anyway, so I would like to tell you a little bit more about groups in Magma, essentially. And what I usually would do is, there's a certain type of group, it's called J2. I will come back to that in a second, but let's just open the online calculator so you can just access it in the following way. So there's the J2 comes from the Atlas notation. So Magma is always using the Atlas notation. If you don't know what the Atlas is, we just open Google. Atlas, finite simple groups. I should learn spelling. Spelling is very difficult. I should learn it eventually. And you will actually find the Wikipedia page. And there's a very, very famous book, which is called the Atlas of Finite Groups. And the notation in that book is what is used by Magma and all the time. And there is a certain group that is called J2. We can't go to that in a second. Let me just set it up. G is defined to be J2. And then you can ask something like whatever. Character. Well, let's just ask what G is actually. Let's just ask what G is. So G is the permutation group on a set of cardinality 100 defined by those two permutations. We'll see the set of cardinality in 100 in this video, but this is just what G is, G. And maybe you can do more fancy things, whatever, character table G or something like that, and you will get whatever it is, large character table. Anyway, the point of this kind of part of the lecture is to set that up in Magma actually. So we want to set up this group J2. Let me explain a little bit about the history. So J2 is one of the 24 sporadic groups. So people are trying to classify finite simple groups. And there was so Mathieu in the mid of the 1850s or something, discovered 5 exceptional groups. And then not much happened for another 100 years. And then Janko kind of discovered 4 of them. They're called J1, 2, 3, 4. They don't have much in common. They don't form a really nice family. Just Janko discovered them and joint work with many, many, many people. And the reason why there is this large gap of 100 years between Mathieu doing it, discovering the groups with the same name, and Janko it's because these groups are usually very tricky to define. They kind of arise as symmetries of certain objects, but the objects you see are kind of finite number coincidences and they're a bit random. It's like really difficult to construct them. Similarly, the big one, the monster, is a symmetry group of a certain Lie algebra, if you want. And it's like really difficult to construct. And I would like to show you this one because it actually appears as the symmetry group of a graph with 100 vertices, and the graph is constructed from the Fano plane. So and it's usually in this setting, as soon as you have the construction, it's kind of not that difficult to verify that you get kind of a special group. But to come up with a construction in the first place is like really brilliant. And I can't really tell you how those people came up with this. They were just staring at examples for a long time. That's what it is. And that sometimes is what you need to do. It's just what it is. Yeah, so great. So let's just get started. So we can set up our underlying friend, the plane, by just copy this nonsense here and just put it into the online calculator. Okay, this is just what it is. And I could ask what is L, for example, and I would get some answer down here. So there's 7 points. So the Fano plane, 7 points, 7 lines. And of course, showed you L, so there are 7 lines. And here are the points, and they are given in homogeneous coordinates. So it's like a projective plane. Okay, fine. Good. So that's the underlying thing. It has 7 points and 7 lines. Plane or plane, always kind of very important thing. And what you do first is, let's just do it up to this point. We set up a certain number of vertices, and I will explain in a second what that is. And we set up a certain graph. Okay, vertices, the -1 just stands for the one that encodes the points. So we have 7 points. So vertices are given by 7 points. The -2s are the lines. So we have 7 lines. And we join them in the following fashion. We join them in essentially setting up something like the planar plane itself. Whenever the point is not in the line, then they are joined by an edge. Okay, fine. And we can ask something like adjacency matrix of this graph that I call G1, and it will be something. Oh, very good. That's what it is. And Magma is not very, very good in outputting some nice diagrams. So I put it in this fabulous graph-online.ru, where you can just go on adjacency matrix, just copy it in. It has the same code, it has the same output, it accepts the same input as Magma has an output, and it just gives me one of those guys. And it's actually quite a nice graph. So it has 14 vertices, namely the 7 lines and the 7 points, and they're joined by an edge whenever the point is not on the line. That's just how it works, and it's directly cooked up from the pane of plane. Note how this works. The graph is just vertically dimensioned. So you just give it a vertex dimension. And like Magma is like really powerful and can just compute something like the automorphism group of this graph. So let's just do it. Compute automorphisms. So let's get rid of the adjacency matrix. And it will show, for example, the composition factors. So again, A17 is kind of Atlas notation. We'll come back to that in a second. And then there's a cyclic group. So it's essentially A17 up to cyclic group factor. Okay, I hope that makes some sense so far. Good. So composition factors does exactly that. And essentially, so let's try what it is. So usually you can run something in Magma like this. So Magma knows certain groups, SL2, SL3 over a field with 2 elements, and PSL2 over a field with 7 elements, for example. And you could ask, are they isomorphic? It's isomorphic, and it will tell you, yes, it's true, but even better, it will also output an isomorphism between them given in the presentation known by Magma. So this is SL3 over a field with 2 elements, and this is a PSL2 over a field with 7 elements. Turns out that they are actually isomorphic. So Magma knows that. So what we can actually try is we can do the following, and this will identify in a second the second output factor for you, 1,7. We can just ask, by the way, this 1,7, so we need to go back to this one here, so we can get the composition factors, take the derived subgroup that gets rid of the Z mod 2, and we can just is isomorphic to our SL32, and this thing means that there are 2 outputs, a true or false, and the isomorphism, and I kind of don't want the isomorphism, I only want the true or false, and I get true, which really is that in our little graph, essentially the automorphism group of that graph is SL32 over the field of characteristic 2. It just is a slightly strange output because it outputs P SL27, which is just isomorphic, right? So it kind of goes with this output. A17, 1 is SL2, 7 is the characteristic. So it goes with this output, but actually what we see is SL32. Fine. And we can kind of look at the orbits if you want under this action. But let's not do it. You get some orbits. So there's even a G set. So Magma even knows the group homomorphisms. So the group action on that space. Very good. So there's some exercises. So let's set up the slightly larger graph. So we set up we already did that in the last video, so I'm a bit faster here. We set up the, what is it called? The flats. The flats. And this is just the following. I just put it here. So I don't need this one, and I need this one. Let's get rid of the isomorphic. We don't need the group. So we just set up another set of vertices if you want. Namely ij for now Pi is in J. So a flag is just a collection of a point and a line that is in that point. And I just set up those flags. So we can now have a look at what those flags are if you want, and you get certain numbers. So 1, 2, 1, 3, 1, 5. So everything is in 2. Every point is in 3 lines. If you keep the picture of the Fano plane in mind that we had in the first lecture, somewhere, certainly we had it. So every point is in 3 lines, right? And that's just what I've set up down there. I should have mentioned that there is kind of the A part of the lecture, and I'm just skipping it. I'm going to the B part. But the A part is kind of a reminder on types in Magma. Anyway, so we define those flags. And now we just join a certain, make the graph a bit bigger. I'm not going to explain that right now. Let's just do it. So I will make my bigger by adding the flags as well. Okay, fine, no output yet. And I decided to, well, here is the graph. I just put in the vertices and the edges, and we'll see in a second what that actually is. Here it is. And now we can ask JSON C matrix of my little graph, G2, and I should learn spelling, I guess. Very good. And it gives me 36 as a very large one, 36, quite a large piece. So that's already something we don't want to put anymore in in a graph, because it just, there's nothing we can see in this graph. It's just too big. But it has 36 vertices, so you kind of don't need this anymore. Anyway, so here's the graph. And it's a bit easier if I just explain what I just did. You can read it in the code. But essentially, it's this picture. So there's an artificially joined point. Fine. And then there are 7 points and 7 lines. So all of these are vertices and 21 flags. And all of these are vertices. And the numbers here indicate. So here, every point is joined to 4 lines, and every line is joined to 4 points. Why? Because I'm just joining the things that are not in there. And every point lies in 3 lines, but there are 7 lines. So there are 4 which is not in, and so on. So here, every point is joined to 9 flags. Yeah, every point lies on 3 lines, and I'm joining it to the flags that contain that point. But then there are more than them, because you have the second point to choose with. And similarly, all flags are connected to 3 points, and here's some similar picture. So this is a graph which is quite large. It's of size 21 plus 1 plus 14, so 36. And we can just ask, what are the group? What is the group? What are the automorphisms of this nice little graph? So here's my little graph. I've already set it up. And I need to make this longer and longer because the graph gets pretty large. Keep in mind, we are trying to construct a sporadic group. So there's a graph that's 100 vertices. That's not completely trivial. Okay, so there's U33 up to the cyclic factor nobody cares for. There's the unitary group 3, 3. And so this was kind of well known for a long time. We have this graph with 36 vertices, and the unitary group 3, 3 is essentially the automorphism group of that graph. And the brilliance is now to analyze, to take U33 and kind of throw in the extra information coming from U33. So we are trying to do that now. And it turns out that there are, 63 additional information, and you add in another dummy vertex, and then you get 100 vertices. Okay, so before we do that, let's just do it. So we can set up a standard Hermitian form. So it's a unitary group, or the special unitary group. So there's an Hermitian form on a 3-dimensional space, and we can just set up the standard Hermitian form on that space. So Magma knows all of that. Very good. It's given by this pairing matrix. We can just do that, no problem. And sigma is a certain map on the ground field. Let's ignore sigma for now. Sigma is a bit tricky. In the original video of Don, we had a long discussion what sigma actually is. It's kind of nice to revisit that in case you wonder about sigma. So sigma is in certain involution of the ground field, and the ground field here is a ground field with 9 elements. Okay, fine. So let's set up. We already know J, and we can set up a unitary space defined by sigma, and we can set up the unitary group, and we can just do this. And they are the for all. Why are these guys here? I need to fix that, I guess. For all G in the generators of the unitary group, we want isometries of that unitary group on that space. for all, is there some isometry, and that's what this code does. So essentially we will add the isometries given by coming from the unitary group. And we just can set that up immediately in Magma. So we can do, for example, this if you want, and you will get some results. So there are some isometries, and there are some points with the dot product that we get rid of. Yeah, well, we can leave it here. So we define a vector and another vector, cast it in my little space, my unitary space. So I need to cast it into that space. And the dot product of u is 0, because we remember how the matrix looks like. We can output the matrix as well. So the dot product of u is 0, and the dot product of v with itself is 1. So we have those two different types of vectors. We have more of them. And some of them have dot product 0, and then the others don't have dot product. They have dot product 1. So we have the isotropic and the non-isotropic subspaces in this space. And it turns out that they afford a representation of dimension 36. So the non-isotropic ones for the dimension of the space of dimension 6,3. And we can just check that as follows if you want. So we can set up the isotropic representations as follows. So the isotropic is a subset, well, conjugates of u's, this just means conjugates, and the other ones are the conjugates of v. And we can just have a look on, again, I copied this wrongly. This should be this scrap. And then one of them has order 28, and the other one has order 63. The total number of subspaces would be 91 in this case. So the isotropic subspaces kind of conjugates of the vector v. Conjugate is indicated by this, well, this little hat of u, and the non-isotropic ones conjugate of v. And one of them is of order 28, and the other one is order 6,3. And Magma can do that like immediately for you. It's kind of built into Magma. And the point is now that it's kind of really brilliant. Now you throw in this representation of those isotropic vectors and construct a new graph, which looks like this. So this is our old graph. And now we construct a new graph and throwing in those additional vertices and it's kind of a dummy vertex. And if you do the calculation, 6,3 plus 3,6 plus dummy, that's 100 vertices. And that turns out to be the graph. And it works as follows. So we take the edges like this, and well, let's do it. So fine, we have set up this one. So now we can, we don't need the composition factors anymore. We take the edges, fine. There's a new edge set, edges. Just a new edge set. There's a lot of edges so far. Fine, we will massage that anyway. Let's ignore this set. Okay, fine. But I hope it's kind of clear what we want to do. We want to throw in those 63 vertices. And let me just run something. We just act on itself, and we have a certain condition. This is a fun one. Exists T will do the following. It looks for an element that satisfies the condition, and then if it finds one, it defines T to be that element. So actually, I have a T now. So I can actually output the T, right? So it found the permutation. It is the following: C in classes of M3. So here M3 is just my automorphism group of my graph with 36 vertices. And well, C1 should be equal to, and C2 should be equal 63, right? So that's exactly those ones where I pick out something that is in a non-isotropic world. And I ask it, does it exist? And I take the first one that exists. So that's essentially what this command does. Okay, takes the first one that exists, and then I just take that one and throw in the conjugates, exactly mimicking the construction from before with my v, just now completely in the setting of the graph itself. I take the conjugates of that one. Fine. I still get the true because I still have my exist here, but let's ignore that. I take, well, so this is just recasting it, nothing happening. So let's have a look at x here. And then let's recast it and let's have a look at x again. Okay, so this is a set of a lot of elements, and then I have a list of a lot of elements. And we can actually ask how many elements there are, let me get rid of the set. Oops, sorry, let me get rid of the set. We can ask how many elements there are, and there should be 36 exactly. So these are our new points. I just set them up exactly following the strategy from before, just directly on the graph. This is really just throwing in the isotropic vectors under this action of U33. Okay, and I just joined them under the, well, I just make my edge set bigger exactly in this fashion that things are joined as in this illustration, and I just do it in Magma. Right? Do it for you, Magma, and come out. Nothing happened yet, so just make my edge set bigger. But I can try now something like this, and it has quite a few things going on. It's quite large right now. Very good. I just joined them together. There's a lot of edges right now, right? 1,000 something edges. Cool. And what I will do is I just join the corresponding ones of the corresponding order. I'm not going to explain that, but you can just do that to make it even bigger to get the correct number of edges in this thing. So let's see again how many we do, how many we have. Now there are a lot of edges in this beast. So the graph that we construct is actually really, really large. And we can just do the following. This one here. So these are the edges of our graph, and I just add now, not much is happening now. I just add vertices that I call 1 to 100. I just relabel them. These are my vertices, hundreds of them. I first join even more edges. And then the edges is exactly what gives this graph, the so-called Pauwels graph. And this one has 100 vertices. It's like tremendous Pauwels graph. And I'm doing this because it's large, it's too large, right? So let's not output it. Fine, there's 100 vertices. I'm doing this because all quadratic groups arise from similar constructions, and it's always like a miracle that it actually works. So we take the Fano plane, we beef it up using the flags. So that's what we did last time already. And then we add in 63 new vertices coming from non-isotropic vectors of the acting graph automorphism group, which is U33, and join them in some funny fashion and get this graph, which is like tremendous. And maybe I should just, it's now called Pauwels graph, that's fine. And then we can ask Magma about properties of the automorphism group of the Pauwels graph. And it turns out that this one is essentially our friend J2, right? It's ZMod2 extension, but who cares? And kind of Magma is less ridiculous. So if you write time in front, it will tell you how long it took it for this. So it took it 0 seconds, 0.00 seconds to compute this automorphism group, which is actually a very large group, because we can also just say something like number of elements of that fucking group, and it's a very large group. It has whatever, how many elements, more than 1 million. We can output that funny thing, and is exactly our friend, the J2 group from before, acting on spaces, but it has a slightly different presentation now. But we could still ask something like character table of that funny beast, and Magma is actually able to do it, although it's not doing this from the database, right? I just set up this group of just as it is, and it can compute the character table in like no time at all, which is like absolutely ridiculous. 0.1 second. Wow, that took a while. Anyway, so this is how you kind of set up large groups and large graphs. As I said, they are already in, so let's compare which one is faster. Group J2, okay, and then character table, time, and character table. So let's see which one is faster. So now it pulls up the group from, this one was actually slower. Now it pulls up the group and then computes its character table. So those groups are all built in, but I just wanted to show you the construction of one of the sporadic groups. And all other sporadic groups are kind of constructed in the same way, just the graphs get even more fancy. I hope it was reasonably clear. The only point you need to remember is that Magma can do all of that fun stuff for you, even finding isotropic and non-isotropic vectors. And essentially what we did, we had the Fano plane, we joined the flags to the Fano plane, and we joined then this isotropic representation, which comes from the automorphism group of the graph we get was a unitary group. Cool. So let's have a look at one more topic in group theory, one that I really like, the group determinant. So that was what Frobenius did instead of representations, and I would like to write it down for you. So it works as follows. You take a group, let's say finite group of order n, and we have one indeterminate for every element of the group. So there are a lot of indeterminates. And you write down the matrix given by this product, so GH inverse, that's now a G by G matrix, where G is the order of the group, and you ask for the group determinant of that beast. So let's have a look at an example. We take the dihedral group, so now we can just run it here. We take the dihedral group of order. So what is the order of this beast? The dihedral group groups are of order 8. That's why I call it D8. Okay, D8, we take D8, and okay, fine, and define the following function, which we call group determinant. So let's see what this does. Let's just put it here first. Group determinant takes a group, okay, fine, sets up the polynomial ring, like the variables in the order of the group, and does just assigns exactly the corresponding index and computes the determinant and factorizes then the determinant. So this is the function, and I did it for D8, obviously, and I decided to erase D8. So let's put in D8 again, our little dihedral group. So let's see what the function actually does. I need to put it here, and it should output the group determinant. So let's have a look. So right now it's just a matrix. It really just sets up the 8 by 8 matrix. And then you can see here return M and determinant M. So I actually have two outputs, and I can actually produce another one by just doing something like this. Okay, so the second output is now D. Okay, this is B, and D should be probably really, really, really large. So this is the determinant, like large. And now we can try something like factorizing it. I should factorize B here, I guess. We'll see what happens if I factorize B. That probably doesn't work. That's correct. So maybe let's factorize B, see what happens. And this is my factorization. And it picks out exactly let's do that. Character table of D8. It picks out exactly the irreducible characters. So let's see. So the character table has 4 one-dimensional ones and a 1 two-dimensional one. And you can see them here as well. You have one-dimensional ones. They appear of orders. This is the order with which they appear. And you can kind of see the pattern of the signs here as well. And this is the two-dimensional one, and this is the factorization of the group determinant. So maybe let's do another example. Maybe let's just say symmetric group. Symmetric group, and maybe let's not do it too big. And I just keep it D8. I don't care anyway. So I get now one-dimensional representation by factoring it, a one-dimensional representation, and a two-dimensional representation, which fits exactly to the character table. And the fun fact is that this is what Frobenius did when they discovered what representation theory is. Really just factorizing this beast. And you can try that with larger things. We have done that here down for example, for the quaternionic group, and you can factorize it. And here it's actually set up correct, and you get something, but it's actually really, really slow. So let's just try. So this one is interesting. So let's do the alternating group. And let's see how long that takes. So here, let's get rid of the character table. I'm only interested in factorization, because this is actually, well, this was kind of okay. But what happens if you take the alternating group? So we can just write alt4 and do the same. And I'm almost already won. So last time it took 36 seconds. So I need to fill some time now. How are you today? So I'm varying something red. And I'm waiting for Magma to finish. So the point here will be that actually factorizing group determinants is like super cost invasive and expensive, because you need to factorize a big thing, and it even didn't work. So, current total memory, okay, fine. So this was actually already too big. Yeah, there you go. It doesn't run in the online calculator anymore. Now we have an example of something that doesn't run in the online calculator. So make the group a little bit smaller, and then hopefully in this case, it does it in node time. Anyway, so we also have the example of something like, where was it? Like the quaternionic group. Fine. So let's try that one. Defined as quaternionic group. And let's try, and this doesn't work. Fine, that's fine. We can do the following. Small groups, small group, 8. I'm not quite sure which one the quaternionic group is. Let's try this one. Possible that this is the quaternionic group. Maybe this one is actually the quaternionic group. There you go. So one of them, this is interesting. So one of them is the dihedral group. So they have kind of a very similar behavior, and one of them is a quaternionic group there, but they have slightly different factorizations, as you can see. So although the character table is the same, the factorization is somewhat different. Anyway, so that's what Frobenius did, factorizing those representations, and then discovered representation theory. And we have kind of this running example. And the alternating group apparently doesn't run in the online calculator. So last time I thought I got this result, but anyway, apparently it doesn't run. So eventually you need to come up with a better strategy of doing it. Let's just do one more example. So yes, remember that small group just picks out a small group of the order I give it, and then the third number on this list. So maybe let's try this one, hoping that this won't blow up, and then we are good for today. There are many more exercises and everything in the file. Anyway, this is still running, so I still need to tell you again that's why it's so brilliant that Frobenius actually was able to do it, because this is actually really expensive to factorize, and again, it doesn't work. So there you go. To factorize those determinants is just a group of order 12, and factorizing the determinants is just terrible because it's a polynomial in 12 values. Anyway, so that's it for today. I hope you enjoyed this video. I hope you enjoyed Magma, and I also hope to see you next time.